We try to understand how an artificial intelligence works. We usually treat it like a static puzzle. But inside a running model, it looks more like an active, continuously shifting labyrinth. We can see inputs entering and outputs leaving, but the actual journey through the maze happens in the dark. Most AI research today focuses on mapping static circuits, the anatomy of the model, or grading the final text it produces. We spend nearly all our time on the physical structure and the end product. This focus creates a gap in our understanding. In a phenomenon called the hallucination mirage, an AI will output a confident lie. If we only evaluate the final sentence, we miss the internal computational tension and entropy collapse that signaled the error before the first word was written. To understand why a model fails, we have to look past the static anatomy and study the system's physiology, the real-time operational dynamics as it wrestles with a prompt. Machine psychology is the study of these internal dynamics. It uses operational signals, measurable computational quantities like activation pressure and attention tension, to define the mood of a running system. These states are entirely quantifiable. When multiple data pathways compete for resources without resolving, we can measure that conflict as agitation. When a model's attention rigidly locks onto a narrow set of variables, we identify that drop in diversity as fixation. In a trial known as Test T08, researchers extracted the model's internal state factor at generation step 5, the moment right before the output is finalized. By reading that early signal, they could predict if the AI was about to lie or contradict itself before it committed to a single token. This chart shows how internal states dictate answer quality. In a calm state, it hits 91% factual accuracy. But look at the far right. When representational layers fragment into disassociation, that accuracy drops to 44%. These signals are highly predictive, but they lead to a much larger question. Is this internal organization a quirk of one specific chatbot, or are we seeing a universal law of how transformers process information? To find out, researchers designed a stress test. They took the machine psychology framework and applied it to 3 radically different architectures: a mathematical theorem prover, a code generator, and a model trained entirely on genomic DNA sequences. The initial results looked like a failure. When they compared the raw internal data of the language AI directly against the math AI, the predictive accuracy dropped to 0.20. It was identical to random chance. This scatter plot shows why. It maps the internal coordinate space of the language model, the circles on the right, against the theorem model, the triangles on the left. There is zero visual overlap. The two systems appear to speak entirely incompatible internal languages. It seemed to confirm a bleak theory, that every AI species is a unique alien entity with no shared internal organization. But the researchers hypothesized that the organization wasn't missing. It was just being expressed through different geometric coordinate systems. To test this, they built a 3-stage observational architecture. Step 1 requires inferring the generative regime, categorizing the broad rules the model is using to process data in that moment. Step 2 uses that regime to normalize the data, stripping away the noise inherent to that specific model's parameterization. Step 3 is cross-model alignment, translating these disparate coordinate systems to match each other's frame of reference. When aligned, the accuracy jumped to a perfect 1.00. The DNA, code, and chat models all revealed a shared geometric structure hidden beneath their different coordinates. A moment of wonder. This suggests that despite radically different purposes, these artificial intelligences naturally converge on the same underlying patterns when they process information. But this shared geometry isn't an all-or-nothing phenomenon. Researchers use these results to build a portability map, showing how this internal structure changes as models become more specialized. The map reveals a hierarchy. The coarsest layers, the broad regimes, are universally identical across every transformer model tested, from text-based language bots to complex genomic sequencers. but the finer, more specific family states degrade the further you move from text. They remain highly recoverable in code and DNA models, but they compress into simpler binary shapes when tested on visual image generators. This gradient provides a staged map of how internal structure travels between different types of AI. It shows that MachineBot follows measurable, hierarchical rules, identifying exactly where one model's organization stops being portable to another. Understanding these rules allows us to shift AI safety from a system of reactive filters to a practice of proactive interception. This is the ethical layer, an early warning system that reads an AI's internal geometric pulse while it is actively running. By utilizing the machine psychology framework, safety protocols can detect the structural shapes of overconfidence or mode collapse in real time. Instead of waiting for a dangerous error, we can use this universal geometry to intercept a hallucination before a single word, line of code, or DNA sequence is ever generated.